In the previous classes, maybe 2-3 classes, we've been looking at flow over a flat plate and the boundary layer that forms over that. We see that the solution, the Navier-Stokes equation can be simplified. And then once we have the simplified form of the Navier-Stokes equation or the momentum equations, then we can use or solve that using the stream function approach. So we introduce that. We also assume that there is similarity, and that helps us to obtain a solution. The solution turns out to be in the form of a series. Okay, so that is not something which is very convenient to handle. Okay, that is, but in principle, we have a solution. In fact, not in just in principle, we have a solution, which is actually very, very accurate and supposed to be describing the boundary layer for our laminar boundary layer over a flat plate under free stream boundary condition, under incompressible flow conditions very accurately. So that's basically what we have. Now, we also said that because boundary layer thickness is so difficult to sort of, or not difficult, but maybe there is ambiguity in where exactly the boundary layer thickness is. So sometimes to avoid that issue, we go in for integral parameters, which are like your displacement thickness and your momentum thickness. And then we said that there is an integral form of the boundary layer equation, okay, where okay, so let me just sort of say that, okay, what we have planned to do today and the next class, and where do we want to go from here, and then maybe we'll come back. So, so we have been essentially looking at these boundary layers solution. We have taken the special case of dp dx is equal to 0. So in today's class, we will talk about if dp dx is not 0, what happens. We are not going to do a detailed analysis of that, but in principle, we can get a few important information from the equations, which is what we would like to understand. And we will play 1 or 2 videos to sort of explain, I mean, through videos also it will explain how the boundary layer separation happens and so on. Because boundary layer separation is a very, very important topic. And from once we understand boundary layers, we go from here to understanding if there is a pressure gradient, what happens. And this pressure gradient is what leads to boundary layer separation. So we will see that's the sequence in which we will move. Now that is once the boundary layer separation happens, then we typically the flow would transition or can transition, let us say, to a turbulent flow. So we will take up turbulent flow as the next topic in this course. Okay. So this is, and I think the remaining 5 lectures is what we have after this. All I think everything will go in the turbulence part. So we will maybe look at a turbulent boundary, laminar boundary layers a little bit, or laminar jets, which are having like a boundary layer sort of an equation, and we will talk about turbulent jets and such things. Okay, so I think that is all that we will be able to cover. But turbulence, I understand a lot of people want to know turbulence or understand turbulence, so we will spend a decent amount of time covering that topic in this course here. Okay, so that's the plan for the next few classes. Okay, now coming back to our equation. So we are looking at integral form of boundary layer equation. So we are saying that our governing equation are so this is our governing equation, and we integrate this equation from integrate with respect to y from 0 to delta. Okay, now once we do that, we will see that we will get an integral form of this equation, which is what we derived in the previous class. So we said that this equation, this term is reasonably straightforward to integrate, okay, because this will essentially change to, so here you can see that if I integrate it from 0 to delta, okay, or 0, so then it will become a simply shear stress at the wall. Now this term is also easy to understand because we know that pressure along the x direction would be related or is related to whatever is happening outside. So between these 2 points, pressure between these 2 points. So we have already seen that because dp dy is equal to 0, so whatever is the pressure here is the pressure here. So if this is P1, this is P1, and if this is P2, this is P2. So when we say that the pressure difference or the pressure gradient in the boundary layer, we can as well go to pressure gradient in the free stream, okay, and we can see there whatever is happening. And in the free stream, why we want to go to the free stream? Because there the Bernoulli equation applies, okay. So there we have P by rho plus u square upon 2 is equal to constant, okay, which gives us that dp dx is equal to minus rho times u times du dx. Okay, and this is what we can substitute in here, and we simply get this is d u times du dx. So till now we have been saying that u is a constant, but in this case now when we are looking at a pressure gradient, we are saying that u is a function of x. The free stream velocity itself is a function of x. And we can see how it is related to pressure gradient by examining this equation. If du dx is positive, it will have one value. If it is negative, it will have some other value of, I mean, the sign will change for dp dx, okay. So one will be like favorable pressure gradient, one will be adverse pressure gradient. So this term is reasonably straightforward to handle. Now when we looked at the left hand side, we said we are not going to do too much to this term, we will only be trying to manipulate this term. And if you do that, so we started off by saying u v times dou u dou y, integrate this with respect to y from 0 to delta. So you say that this is u times this term 0 to delta minus u times dou v dou y dy from 0 to delta, right? And then we say that, okay, this term is going to be easy to evaluate. We get it as uv evaluated at 0 and delta. So at 0, both these two terms are both u and v are 0, so this will go to 0. At delta, u and v are not 0, so v has to be evaluated at delta, which is what we did. So we said v at delta is equal to dou v dou y dy evaluated at 0 to delta, and we use continuity equation dou u dou x plus dou v dou y is equal to 0 to evaluate this term, which was essentially replace this with this 0 to delta and so on. So we did all these manipulations in the previous class. So these were some of the key steps that we did. And once we did all this and put everything into that momentum equation that we have, we got an equation which looks like d by dx of u square times theta plus delta star times u du dx is equal to tau w upon rho. Okay, so you can see that all these integrals that we are introducing, some of them are not going to go away, but we already have defined thetas and delta star in terms of integrals. Okay, so these integrals, I mean, essentially they will become the same as these integrals. Okay, so this is the equation that we would have, and so this is the equation that we can work with. So this is like the same as whatever we have written here, but now it is in integral form, although we don't see the integrals very explicitly here. Okay, the integrals are actually hiding inside this theta and this delta star term. Yeah. These U's are all capital U's because the small U's do not make sense here. Okay, these are all capital U's. So you can see that this is in some sense a small approximation, you can say, but a reasonably good approximation to this equation. Here is what we have here. Now, how do I use this equation? So this is what we are going to see next. Okay, any questions here? So this derivation, again, you can go back and complete if you are not. It may be a good idea to go back and complete it for yourself because we have only looked at a few steps or given you the key steps. So let us say that we will introduce this method, which is essentially going to use this equation, and we will see what we get out of it. So earlier, the basic issue was when we solved the equation exactly from differential form was that we got a series which was very difficult to handle. Okay. So now what we are trying to do, this method is, this is all approximations. So what we are trying to do is, can we get a good approximation without having to handle a series? Okay. So what we are going to do is assume, and there is no basis for this assumption for now. So assume velocity profile as U by capital U is equal to A naught plus A1 eta, this A2 eta square plus A3 eta cubed plus A4 eta 4. So you will see similar sort of a thing if you have seen your homework. We have given you something similar to this. So we are actually solving it for a much higher polynomial. Okay, and then once you understand how to solve for this, you can solve for a lower polynomial. Okay, but what is required is what is the hierarchy of conditions that we use and why should we use them. That will become clear because here we will be using a lot more conditions. Okay, so we have assumed, as we said, we have simply assumed this velocity profile that it applies, where eta we have already know is like y by delta. So this is like a fourth order polynomial. How many coefficients are here? 5 coefficients are here, and so we need how many conditions to evaluate them? 5. Okay. So what are those 5 conditions? So we will have to write it down. So this is given to us. Beyond that, there is nothing which is given to us. We are trying to look at flow over a flat plate. So in a flat plate, what happens? So what are the boundary conditions? At y is equal to 0. So that's the first boundary condition that we can write, that the flow has to satisfy the no slip condition. Okay, so that means that y is equal to 0 when eta is equal to 0, then u has to be 0. So that is the first condition, and whatever is the polynomial, so you can see that this condition I have to always impose. Now what is the next condition that I can impose? Right, so at y is equal to delta, which means eta is equal to 1, I get u is equal to capital U, okay, or which means in non-dimensional form this has to be 1. Okay, this is, of course, this is only approximate. This is like 0.99, 0.95 or whatever. Okay, but this is we are just assuming it as 1 rather than taking it as 0.99. What else do we know? So at y is equal to delta, so maybe you can plot the velocity profile. So this is my boundary layer at any cross section. This is how the velocity profile looks like. Okay, so you are saying that at y is equal to 0, this is x direction, this is y direction, this is u component of velocity, this is my plate. Okay, so at y is equal to 0, you get velocity as 0, y is equal to delta, this is my delta. Okay, so this is what I get. Okay, so now at y is equal to delta, what else can I say? I can say that the slope has become very small, effectively 0. Okay, so that's our condition that we are going to say. Du dy is equal to 0. Okay, so you can see that these are the conditions that I can give, but I need 5 conditions. I only have 3 conditions. So what else? So I still need 2 conditions. Okay, so that's a condition that we can use. Okay, how do I get that? So the fourth condition that is being suggested is that at y is equal to 0, we get dou to u dou y2 is equal to 0. Does it make sense? This condition makes sense? How do I get this? Okay, so there is no pressure gradient, and then you are saying that if I consider at y is equal to 0, then I will get u is equal to 0 and v is equal to 0, and therefore this is equal to 0. Is this correct or is this an approximation? So what are you doing is you are applying your your governing equation. This is a governing equation. You are applying your governing equation at the boundary. Is that correct or is that not correct? No, that's incorrect. Okay, so you should know that it is incorrect. Okay, but we do still apply it because then it is an approximation. Okay, so never apply your governing equations on the boundaries. That is why on the boundaries we have a separate condition, which is your boundary conditions. Okay, so your governing equations are not applicable to your boundaries. Okay, but we are going to, as we said, assume that this is applicable, and therefore we are going to use this. So this is my fourth condition, but you can see that I still need another condition. So we are going to say that, so look here, what else can we say? So here you can say that my slope is 0 at y is equal to 0, at y is equal to delta, my slope is equal to 0, okay, and curvature is also 0, is essentially just becoming very flat there. Okay, so then I am going to say that the curvature is also 0 there. So at y is equal to delta, I get dou to u dou y2 is equal to 0. Okay, So you can see that these are the 5 conditions that we have, and you can say that very few of them are actually exact. Okay, the only exact condition that you have here is probably the first condition here. Nothing else is exact. Everything else is an approximation. Okay. So now I will say we are not going to solve this. I will just say obtain, using these 5 conditions, obtain A naught is equal to 0, A1 is equal to 2, A2 is equal to 0, A3 is equal to -2, and A4 is equal to 1. Okay, any questions here? So I get U by capital U as equal to 2 eta minus 2 eta cubed plus eta 4. Okay, so this is the equation that I get. Now, why did I do all this? So we are trying to find out what is the parameter of interest to us. At the end of the day, we are interested in what is the force which is acting on this plate. Okay, so at the end of the day, that's the basic. So we have assumed certain things. We have assumed that the boundary layer thickness grows in this manner. It just becomes like a 4th order polynomial here. Okay, and we have just evaluated these coefficients when we have obtained this. Okay, but we do not know as of now that how does the boundary layer thickness grows and how does that translate to what is the type of forces or stresses that are going to happen. Okay, so this is where we will have to now use our equations, the momentum equation, because till now we have not satisfied anything. Okay, we have simply said it's a 4th order polynomial, which is fine, and we have said that okay, these are some of the conditions that it should satisfy, and which allowed me to evaluate these unknown coefficients which are there in the polynomials. Okay, so that's all we have said. We have not really brought in the physics anywhere. Okay, there is some physics in these boundary conditions, but not really anything, any basic equation that it is satisfying. Okay, so that is what we are now going to bring in and say that we need to substitute the velocity profile in the momentum equation maybe integral form. So it is clear that we are talking about the momentum equation is d by dx of u square times theta is equal to tau w upon rho. Here is a flat plate with no pressure gradient, so it's du dx is equal to 0. Okay, any questions here? So as a next step, what we have to do is find out theta. So you can see that how exactly, again, we have not, just look at the derivation and just see what is it, that this is what you would get. So now if you look at theta, it is u by capital U, u minus capital U dy 0 to delta, or 0 to infinity in fact. Okay, by the way, once we say this velocity profile is like this, it is implicitly assumed that we are only going till, this is only applicable for y greater than 0 and less than delta. Okay, so velocity will not continuously grow till infinity, or this will not, because this is eta is continuously growing, right? So it is essentially only in this boundary layer region that you are assuming the variation. After that, it is constant, becoming constant after that. So you can nicely put infinity here, but you know that after a point, it will all those variations, there is no variations there, or u by u infinity, u is equal to u, capital U is what we have there afterwards. So you can find out, this is now, once you have u by u, you have to just integrate this, and you can find it out as 37 by 315 times delta. You can find out tau w as mu times du dy at y is equal to 0, and get it as 2 mu capital U upon delta. Okay, so you get, if you were to substitute this expression for theta and tau w into the momentum integral equation, which is at the top, right, you find that we get u square times 37 upon 315 times d delta dx is equal to 2 mu u upon rho times delta. Okay, which gives you, so now you can see that I still need to integrate once. Delta d delta is equal to 630 upon 37 times mu upon rho u times dx. Okay, now I can integrate it with respect to, I mean, you can just integrate this from 0 to x, let us say, and this is from 0 to delta. So I get it as delta square upon 2 is equal to 630 upon 37 times mu x upon rho u plus a constant. Okay, and you can evaluate this constant by saying that at x is equal to 0, your delta is equal to 0, which means that the constant is equal to 0. Okay, so you can get your delta as, so I'm just keeping all this because I want to have some discussion after this on it. So delta is equal to 5.83 times the square root of nu x upon u, and I can find out, or delta by x is equal to 5.83 upon rex square root of this. And if you have to find out Cf, which was tau w upon half rho u square, this is equal to 0.684 upon rex square root of this. So what you can see is that here what you did is very different from whatever we did earlier. What did we do earlier? We did all this effort to actually solve the Navier-Stokes equation. Here, what you did is just first took the integral form of the governing equation, and then you assume some velocity profile, and based on that velocity profile, you have obtained certain things. Okay, so you find that the variation of delta varying as square root of x still comes out. You find that the boundary layer thickness is now increasing as 5.83 upon square root of x. Earlier, you were getting it as 4.96. Okay, so you can find out the percentage difference, maybe 15% or so. And if you look at CF, earlier it was like 0.664, now we have 0.84, 0.684. Okay, so you can see that this is not bad at all, right? So that's the sort of the bottom line. That's how you can use this method, and that's why this method is useful. Okay, because it gives you a very good ready estimate without having to go through the entire detailed maths. Okay, you can actually get a very good estimate of how the things are. Okay, is this understood? Now we can come back here and we can say that, okay, if we had not assumed, so let us say that I assume a linear velocity profile. Okay, so I don't even like this curvature and so on. Okay, so I just assume it's a linear velocity profile. So then what are the conditions that I should use here? So then you can see that I'm assuming that to begin with itself, I'm not including A2, A3, A4, right? Then what I should have is, and I only need I have two constants in that case, and I should use two conditions. So you can argue that I have all these conditions, all these 5 conditions are applicable. Okay, so I should be able to choose any 2 conditions, right? But that is not how this works. Okay, so that's why we said there is some sort of an hierarchy in what we are doing. Okay, so it's like some exact and then somewhat approximate, some more approximate, more approximate, and more approximate. Okay, so that's how you are sort of saying that. So and therefore, when we have to go to, you pick up the most accurate conditions which are required, and if you're not able to find, you try to generate it. The method, like that's why we took a 4th order polynomial and say that, okay, this 5th condition, there was no way to actually get it. We just generated it like that. Now, if you want to go to another term, what will we do? We'll say, okay, the 3rd order third derivative of u at y is equal to delta is 0, 4th derivative is 0, or whatever. So some such condition we will have to sort of impose in order to get to a higher derivatives. Okay, but we do not know what is the implication of that. We will have to check it whether that making sense. But this is the type of things that one can do. Okay, so that's my first comment, that you can choose any order polynomial that you like. Okay, but you have to evaluate your conditions. When you evaluate your conditions, evaluate it in a way that it becomes more logical to take this condition over some other condition. So in an exam, it may happen that, okay, you may do something else, okay, which may not be, and then sometimes people come and argue. That's why I'm just telling you first beforehand itself that, okay, this, if we can write out, if we can use a better condition, then we don't want to use like a lower order condition in some sense, or less accurate conditions in some sense. Okay, so is this clear? And what it also illustrates is there is a trade-off into, if I use a 5th order term and a 6th order term, so is this going to be better than a 4th order polynomial? Yes, no. Not necessarily, right? And why is that? Because I still need to evaluate these coefficients, and these coefficients I will introduce a lot more approximations to evaluate in order to evaluate these coefficients A5 and A6. Okay, so what is the net effect that I have gotten? Okay, and this is the answer to a lot of, even like when you look at experimental data and fit that, and we say we can fit any order polynomial. But the issue is that, can we fit any order polynomial? The same sort of a problem is what we are seeing here. It's a velocity profile, we are fitting it with some polynomial. Okay, you can go to higher order polynomial. Okay, higher order polynomials are supposed to be more accurate, which is fine, but they are only accurate till you can get the coefficients accurately. And you have now no more coefficients to evaluate. Okay, so it may happen that you have to now introduce a lot of approximations in order to evaluate those constants, those coefficients. Okay, so then you have to look at what is the net thing that you are finding. Okay, so it may be the optimal may lie somewhere in between. Okay, maybe if it's 2nd order, 3rd order, even a 4th order polynomial may be far more accurate, as compared to like an 10th order polynomial here. Okay. Is this clear? So this is the second comment that I would like you to make to understand. First comment was to the order in which you would like to pick up the condition. The second one is to look at, going with the higher order polynomial is not necessarily always beneficial, is the second comment that we are making here. Okay, any questions? So this is a YouTube video. It shows you if you have an aerofoil, okay, the boundary layers that is going to form, and then they are going to change the angle of attack and see how the flow is going to happen around this.
As the angle of attack of an airfoil increases, the flow in the boundary layer stops, then reverses direction. This is called boundary layer separation. As angle of attack increases further, the point of separation moves forward on the airfoil until it has so disturbed the flow around the airfoil that further increases in angle of attack produce less rather than more lift. In this condition, the wing is said to be stalled.
Okay, so this is one very simple video. It shows you that how, and it's showing you live as to how the flow patterns are changing as you keep on increasing the angle of attack. You could see clearly that there was no flow separation to begin with, but with, after some angle of attack, you could see that there is a large region of flow separation which is forming, and then you also get to a condition of stall where there is a sudden drop in the lift that we have. Okay. Now let us look at one more.
Hi, my name is Wouter Emery and I'm the founder of AirShaper. In this video, we'll discuss flow separation. In our previous video, we saw that the air close to the surface will stick to it, forming a boundary layer. But in some cases, the air is not able to follow a certain curvature on the geometry and it will detach or separate. Let's look at why this can happen. When you look at the airflow across a flat plate, as we did in our previous video, the free airstream velocity is quasi-constant. Because of Bernoulli's equation, which states that pressure goes up as velocity goes down and vice versa, this means that if the velocity is constant, the pressure is also constant. This means that the pressure gradient in the horizontal or x direction is almost zero. Also, the pressure inside the boundary layer is actually imposed by the pressure in the free stream velocity or free stream airstream above. This means that the pressure gradient in vertical direction, away from the surface, is also close to zero. But if the air moves across a curved surface, it will start to speed up and slow down. Take the flow around a cylinder, for example. At the front face, the pressure is the highest.
Okay, so this is a case that we would like to discuss or you to understand clearly. Okay, so here what is happening is that is a curved surface, is a cylinder, let us say a circular cylinder. So in the first part, what is happening is you can think of that there are a lot of streamlines which are there, and then these streamlines have to, one streamline is deflected or the streamlines are deflected. So in the same region, the flow, there are far more streamlines that you have. So you can draw a streamline which is very far off, let us say which is more or less parallel to this this line here, this axis here. Okay, so between these two, so that line and this line, you can see that there were so many streamlines. Now here, the distance between the streamlines as you go at the top of the cylinder, again you are having that streamline very far away. But you can see that from that far away streamline to this point on the surface of the cylinder, the area has reduced, and therefore all these streamlines that you had earlier and in this region are now passing through the same region. So that means that the distance between the streamlines have reduced, which means that the flow has to accelerate. Okay, the flow has to accelerate means, so you can see that this is the condition, dou u dou x is equal to 0 now. Now, if dou u dou x is equal to 0, we have already seen that from the Bernoulli, and again an equation which was written, now it has been removed. Okay, you find that dp dx is less than 0, right? Should we write down this condition again? It's just p by rho plus u square is equal to constant. So if you look at dou u dou x, if it is greater than 0, then it will lead to dou p dou x as a negative. Okay, so that's where it is coming from. So if that is the case, so you can see that there will be an accelerating flow in this direction and there will be a dou P dou x, and this, and what does it mean? Dou P dou x is negative, means pressure is more here as compared to pressure here, okay, which means that pressure is pushing the flow in the same direction in which the flow was happening, okay. So it is an aiding, so it's just called as a favorable pressure gradient, it's just favoring the flow, so there is nothing wrong with that. So although dpd, so here you can see that the dou P dou x is negative, this is what is known as a favorable pressure gradient, okay. Now on the other side, before even trying to analyze, what will happen is once you go from this point onwards to here, whatever we have said, the reverse of that would happen. Now the streamlines will expand out again, so therefore the flow velocity will reduce, therefore you will get dou P dou x, sorry, dou U dou x is equal to is less than 0, okay, and from Bernoulli now you will get dou P dou x is equal to 0. So that means between this point and this point, pressure is now increasing from between this and this point. As you increase x, your pressure has to increase, okay. And so now the pressure gradient is now against the flow. Flow is trying to move from left to right, the pressure gradient is in the opposite direction, okay. So this becomes an adverse pressure gradient, and in the region of adverse pressure gradient, the flow separation happens. And why the flow separation happens is the flow, the region, wherever the fluid momentum is not strong enough, is not large enough to be able to keep on moving, because you are applying an opposing force. So if you have an opposing force and the momentum is not large enough, then the flow will start moving in the opposite direction, okay. So that's what we will see.
From there, it starts to curve around the cylinder, speeding up, creating a drop in pressure. Now, as the pressure drops with increasing distance traveled x, we can talk about a negative pressure gradient, which is good. The airstream is actually being pushed forward by the pressure delta, and this helps to overcome the friction generated in the boundary layer, which gradually grows thicker. The maximum velocity is typically reached somewhere around the midpoint of the cylinder, after which the flow starts to slow down again. This means that the pressure gradient is now reversed. It's a positive one, because as we move across the surface of the cylinder, the pressure goes up. And this is what we call an adverse pressure gradient. The flow is no longer driven by the pressure gradient, but actually obstructed by it, because the airflow now meets the flow into regions with a higher pressure. If the pressure gradient in the horizontal direction is positive or 0, as in the case of the flat plate, then the velocity gradient.
Okay, so this is the next thing that we would like to discuss, okay. Actually, really speaking, this illustration is pretty good here, and this is going to be the same sort of an argument that we just used in order to obtain the boundary condition at the very top, which is written here, okay. So there we said that if we want to look at why should the second derivative of velocity should be 0 at the wall, we said that we go to the momentum equation, and in the momentum equation we set u is equal to 0, v is equal to 0, okay, and that gives us that the second derivative of, or the viscous term is 0, right. So that is the condition, that's how we are getting. Now when we have a pressure gradient, what would happen? So let us just see that, and that is the argument that is being made here. Okay, so now what we are saying is that at the wall, if you go to the wall, again we are saying that, okay, now we are retaining this term, and we have seen that dou P dou x could be positive or negative, okay. And so if it is negative, which is the first case here, okay, we can see, okay, at the wall again, we are going to argue that these terms are not there. So if we apply this equation at the wall, which we said is not correct, but we are just going to apply it nonetheless, okay. So we can see that these two terms remain, okay, and what this term is going to give me is the curvature. So you can see, sorry, this is y, So you can see that this is going to give me the curvature of u at the wall, okay, which is going to be now dependent on the gradient, what is dp dx doing. Okay, so if it is positive, negative, 0, depending on that, we will have different curvatures, and which is what is being plotted here. So you have to just look at the curvature of the velocity profile at the surface. So normally what it is for a gaseous profile, is the curvature positive or negative? So you can just see that this is my velocity profile, this is my u by capital U, which is going to 1, and this is my y. Okay, or if you want to plot it in the other way around, u by capital U. Okay, maybe if you want to plot it the other way around, this is my u by capital U, which is 1, and this is how my profile is asymptoting to 1. This is at y. Okay, so you can see that the slope is continuously reducing. Okay, so the slope is continuously reducing means the curvature is negative, right? Just a negative curvature, that's what you are looking at. So normally you would have this is the negative, and okay, so maybe we can, and in the other case, so now when dp the dx is going to be, so let's see if let's see this correctly. So we are saying at the wall, we are getting nu times dou to u, dou y2 is equal to 1 by rho dp dx. Okay, so I have gotten rid of these two terms in the equation, and I have equated these two terms at the wall. So this is what I will get. Okay, so now you can see that when dp dx is negative, the curvature at the wall that I need is negative. Okay, and if dp dx is positive, okay, the curvature that I need at the wall is positive. Okay, so negative, and okay, so we can go back to the previous slide and see what was happening here. So you can see that in the accelerating part, dou p dou x was negative, so this was negative, okay, and this was also negative, so there was no issues. Okay, but now what is has to happen when dou p dou x is greater than 0 in the right side, okay, then this has to change its curvatures. It has to change this curvature. So earlier what you were getting is a velocity profile which was like this. So earlier this is what you were getting as u versus this is y and this is u. Later on what we will have is that the curvature profile has to become something like this. So this is u, this is y. So you will see that there is going to be a negative region which is going to be involved, which is like your region of flow suppression. Okay, because the curvature now has to change. So that is the argument that we will come to.
Pressure gradient in the horizontal direction is positive or 0, as in the case of the butt plate, then the velocity gradient in the vertical direction is a positive one. This means that the further you move away from the wall, the higher your velocity. But if the airflow has to move against an adverse pressure gradient, this will push back the velocity profile, and this reduces the velocity gradient at the wall. At some point, the velocity gradient at the wall will become 0, which is the point where the flow can detach or separate. Beyond this point, the velocity is 0 both at the wall, because of the no-slip condition, and at the inflection point, which is where the velocity crosses from negative into positive. Anywhere in between the wall and this inflection point, the velocity is negative, which means you have a backward flow. And this is what we call recirculation.
So here he is just right now looking at how the velocity profile is evolving on the surface of the cylinder. Okay, and we are going to with the simple argument that if you look at, because there is an adverse pressure gradient which is opposing the flow, so the velocity at the wall has to start reducing, and then it will come to the point that the velocity at the surface is like 0, the gradient at the surface is 0, and then it will start moving backwards as well. Okay, so that's the statement that is making. Okay, and that is now being shown here more clearly. So when you are in the dp dx is negative, this is 0, and then once you come here, there is a dp dx which is opposing the flow. There's an adverse pressure gradient which is there, which is causing a reduction in the momentum of the fluid close to the wall, and then later on, or as you move further downstream, you will find that there's a region of adverse pressure gradient or adverse flow or a reverse flow which is now being seen.
Will separated or detached flow will now start to surge on top of this recirculation flow, which will increase the thickness of the boundary layer and the weight it takes behind, and this can have a negative effect on gravity. In reality, shapes are typically much.
Okay, so this is sort of the bottom line that we can take from here. Okay, that so you can see it from that point of view. You can see it also from this point of view. Okay, by this argument that we have given here. Okay, that there will be a change in curvature that is required at the surface. Okay, because of the equality between these, which has to be again taken with a pinch of salt. Okay, so if that is true, then this is how the velocity profiles would evolve. Okay, questions here? So the same sort of an argument or same sort of a thing we also saw in the first video. Again, the first video we saw that as the angle increases or the angle of attack increases, you will find that there is a formation of a flow separation region which is there. Okay, which is again related to exactly the same argument that has been here. Okay, now we can go back to this figure and say that y between bluff and bluff bodies, these are all bluff bodies, called as bluff bodies. Now the other type of bodies are the streamlined bodies. So what is happening in the streamlined bodies? So what you can see that in this part, what is leading to flow separation is that this is a dou p dou x which is greater than 0. Okay, that is what is leading to a flow separation. So what can you change the sign of this? No, right? Because the pressure is already maximum here and it has to reduce, right? Sorry, if the pressure is minimum here, velocity is maximum, the pressure is minimum at this point, and it has to increase to the free stream. So that's why dp dx is positive, and you can see that that is going to happen irrespective of of the shape. I mean, this is already given in the shape that the pressure is minimum here, and it has to increase after that. Okay, but what you can do is, what is a gradient? Okay, you can control that. To control that, what can you do? So instead of making it as a sharp change, so you can see that this is the point we are talking about. This is the, let us say, first part of the cylinder. Here the pressure is low, and this has to go to the free stream pressure values. Now instead of, so this is one option that we have, and the other option that we have is to take it out more gently. Okay, so what we are doing is, again, the pressure, let us say, is still P1, this pressure is P0. I still need to go between these two values. Okay, but here I am going over a much smaller distance. Here I am going it over a much larger distance, and therefore the gradient that I would have in the second case is much lower as compared to the gradient that I would have in the first case, right? So that's basically what is being adjusted, and therefore I will now have a lesser chance for the flow to now separate out. Okay, so that's essentially what is my idea of streamlining. This is very, very naively speaking, because we have already said that all these pressures are constant, which will not be the case if I change the shape of the object. But assuming that this is what it is, then I will just assume that I can very simply argue that having a larger length for over this relaxation would have a much lower I mean, that's here, I mean, the pressure gradient is less, and therefore the chances of separation, flow separation will be much less. Okay, and that's why if you look at Venturi, for example, this is an external flow. If you look at Venturi, for example, which is an internal flow, you will see something like this. Okay, so here in the first part, it is very rapid, but later on, it is very, very, you again have a much larger length on the diverging side. Okay, again, you are trying to reduce the gradients over which the pressure, I mean, pressure will recover. So you are just trying to increase this length so that dp dx is reducing now. Okay, it will always, the sign will not change, but what will change is the magnitude. So it's always an adverse pressure gradient that you still have to worry about. Okay, so again, I will post these videos for you. You can have another look at it, closer look at it. So we can come back. Okay, any questions here? Yeah.
dp by dx equal to 0 do not occur at same time.
Yeah, so there are more dynamics to that. In fact, this bluff body flow around a cylinder, a circular cylinder, there are not tens papers, there are hundreds and thousands of papers on it. Okay, so there's actually a very, very intricate, lot of intricacies are there. So we are just trying to sort of give you the sense of it by saying that, okay, that's why I said this pressures, for example, this is now going to be a very strong function of lot of so many other things as well. So coming back to a flat plate, so we have seen that there will be a boundary layer that is forming. We have also seen that as we, the delta by x is equal to some 4.96 upon square root of Rex. Okay, so we have seen that as we go further into the flow, this is my x direction, Rex is increasing, the boundary layer thickness is increasing, and beyond a point, my Reynolds number is increasing, Rex is also increasing. So beyond a point, there will be a transition that would happen. Okay, and you will go from this laminar boundary layer to a turbulent boundary layer. Okay, and this happens over some region, which is the transition regime. Before, we don't talk too much about the transition regime, but I think we should be mentioning that very clearly. There is not a sudden transition, sudden change of flow behavior from laminar to turbulent. There is always going to be some transition region in between, over which this is a region which is far more difficult to analyze, and that's why people want to sort of not talk too much about it. It may also happen that compared to this length and the length which is there, this is a much smaller region, and therefore it is difficult and it is convenient to ignore because it is a smaller, relatively small region, and therefore people don't necessarily talk about this transition region at all. Okay, but you should always remember that laminar to turbulent transition will always happen through a transition regime, and therefore this sort of a picture would apply. Okay, now what we also need to sort of understand is that this flow would be like laminar till, let us say, around 10 to the power of 6 or so, or 10 to 5 into 10 to the 5. So 5 lakhs to 1 million, this is where somewhere in between the transition would happen. Okay, so maybe just write it, let me write it more carefully. So critical value of Reynolds number for transition would be somewhere between 5 into 10 to the power of 5 to 10 to the power of 6. Okay. So till now, whatever we have been doing is all in the laminar thing. Now maybe we can spend a little bit time on looking at the flows in the turbulent part. And now we can see that once the flow, even we have seen the video, the first video showed very clearly that once the flow becomes turbulent, or if there is a flow separation, it tends to become more turbulent. Okay. Now what is, but this is really speaking a loose statement, okay, just because there is some vortex shading or some flow separation region that is forming, that does not mean that the flow is turbulent. Okay, so we will see that there are certain characteristics of the flow that should satisfy, and only if these are satisfied, we will say that the flow is actually turbulent. Okay, otherwise the flow is laminar, but it may be unsteady and so on. There may be other states of the flow which are there. It can still be laminar, and it's just that it is unsteady. So what we will do is maybe look at a few slides on turbulence. So let us start off with a very simple experiment to illustrate the state of the flow. So this is what is known as the Reynolds pipe experiment. Okay, and you can see that there are pipes, the walls of the pipe. You can see these thick lines which are there at the top and the just below where laminar is written. Okay, so that is where, okay, maybe I should point it out with a pointer here. So you can see that these are the walls. This is the wall here of a pipe, and you're injecting dye at the center of the pipe. Okay, so at this state, what you see is the dye is simply moving in a straight direction. Okay, so there is no movement of this dye in the lateral direction, and there is very little diffusion of the dye again in the lateral direction, which is happening. Now, as we said that there is always a transition region, which is what we will see that if we increase the Reynolds number, or if you, in this case, if you increase the flow velocity, you will see that the flow will start moving laterally somewhat, okay, which is now going to be seen here. And this is what is known as some sort of a transition region, or there are some instabilities which are being, which will be showing up in the flow. And as you increase the velocity further, okay, now you can see that there is almost no order that is there, okay, and it becomes like a turbulent flow. Okay, now this is a picture from a very famous book which is known as Album of Fluid Mechanics, and it says that Reynolds experiment, pipe experiment revisited. Now what was being done is that this experiment, or the original setup from Reynolds, was sitting, and somebody decided that we should reconnect that and see whether we can do the experiment again. Okay, they did that. Okay, and what was very surprising is the critical value of Reynolds number that was reported by Reynolds, and the critical Reynolds number that the people were finding in the same setup was very different. Okay, so then the question arises, what is creating this difference? Okay, so what you can see is that when you go from laminar to turbulent regime, it is very, very sensitive to what sort of an upstream disturbances that you are getting. So you can see that if any amount of disturbance is there at the upstream, okay, or which can come from the pipe or the roughness and things like that, okay, it will lead to a transition much earlier. So what was happening was that, interestingly, when Reynolds did his experiment almost 200 years back, and when people redid this experiment maybe 150 years back, I mean after having done his original experiment, there was a lot of traffic in the city, and that traffic was leading to disturbances that was leading to this transition. Okay, so that is the last point which has been made here, that modern traffic was found to reduce the critical value of Reynolds number substantially. So here, when the underlying message here is that it is good to know that to understand that there will be a laminar regime, there will be a transition regime, and there would be a turbulent regime. But if you really want to find out the critical value where the transition is going to happen, that is going to be a very, very tricky experiment for you to do, because it is now dependent on so many external factors. A lot of them are very difficult to control. Okay, so this is the first sort of a picture that I would like you to understand and sort of see that how the flow transitions from a laminar to a turbulent flow. Any questions here? Okay, so now this is another picture that we have. So what it is showing is a jet which is coming out, a fluid which is coming out in the form of a jet. So there is nozzle, okay, and this nozzle, the fluid which is coming out is dyed, and then you are taking one sheet of light. So this is illuminated by a laser sheet. So you can see the diametral plane, the central plane of the jet itself, and you're not seeing anything else. You're only seeing one plane. So it's an intersection of, like, let us say, circle and a plane. So you can see only in that plane. So what you see is a lot of vortices which are forming initially. Okay, these vortices we have already seen earlier in our vortex ring experiment or related experiment discussion. And later on, you see that there is a transition that is happening in the flow. And this is for a Reynolds number of 10,000 that you can see. Okay, so here the transition regions are not very clear. It looks like that there is a very sudden transition. This is a little bit of an odd picture that way. Okay, normally you will not see such a strong sudden transition. Normally there would be certain length over which transitions would happen, and you can actually make measurements. If you were to make measurements, you will see a lot of variation in this region. So what you will see, if we were to describe it more closely, if I go further away from the jet, there will be self-similar regions that you would find. That means that the velocity profiles that you can measure, you can collapse them onto a single curve. Okay, but you will see in this region, in this part of the jet, or in fact, of course, this is all laminar, so there is no reason why whatever we are measuring the turbulent region should apply here. But let us say in this part of the jet, you will not find the collapse. Okay, here there will be no collapse. So that is sort of an indication that the flow is adjusting its state from the laminar state to the turbulent state. Okay, and over some distance. Now this is another example of what you can see. If you have now, instead of one cylinder, one object into the flow, you have multiple objects which are there in the flow. They can be arranged one behind the other, like what has been shown here, or they can be arranged one besides the other. So this is one of the first things that I was doing after joining here. This was like 20 years back, around 20 years back, these simulations we were doing. And you can see that the vortices are being formed from the cylinders, each of them. And then there is all very nice interaction that is also happening between them. We will not get into the interaction part of it, but you can see that there are vortices that are forming from each of these bodies. Okay, so vortices are a central part. Okay, there can be a transition. Okay, in the transition region, transition to turbulence in the transition region, there could be like non-collapse of the velocity profiles or non-self-similarity behavior. So those are some of the points that I have mentioned here. Now, if you were to look at the time series, so now let us think of that. I come back to this point, to this experiment. I put a probe in there, and that probe is measuring me how things are varying as a function of time. Okay. So in the first case, you will find that I will not find any variation. It is just constant. The second case, you will see that I will now start to see some sort of an instability, some sort of a variation. Let us say velocity is a function of time I'm measuring. So I will start seeing some variation in velocity as a function of time. Now, by the time I come here, a turbulent flow, you will find that there will be a lot of variations that will be there as a function of time. To give a sense of that, and similarly, if I were to do the same experiment here, again putting a probe somewhere and looking at how things are varying, you will find that it's a reasonably periodic variation that you would find. Okay, and now once you bring in multiple bodies, etc., you will find that that variation is changing. So we are just trying to look at, in the first case, you will find that there is a very nice sinusoidal signal. That's what you would get. Now, once you bring in additional objects, or if you have transition. Now, so what I'm trying to show you here through some representative signals, and these are all like actual signals, actual computations or measurements and such things. So these are real signals. I'm trying to make up a signal here. Okay, so what I'm trying to show you is that what happens when you go transition, let us say, from a laminar to a sort of a turbulent thing, you will find that signals are very, very periodic to begin with. Okay, and then you will have some sort of an intermittent behavior like what has been given here. You can see that it is far more complex than simple sinusoidal. Okay, and then once you go to further, again, let us say increase in Reynolds numbers, and you can see that this is the type of signals that you would get, and even more complicated than this. Okay, so this is giving you a sense of how the transition is happening, because we are now trying to talk about turbulent flows, okay, which are far more complex than laminas. I'm just trying to introduce how exactly what changes and how things are changing in there. So what one would do is look at the how can you analyze this signal? Anybody? Yes. So you can do a Fourier transform, and that will give me, in this case, what would I expect to get? Yeah. Yeah, so here you will get that there is a single peak. Okay, there is a single frequency. Okay, so you will get at all frequencies amplitude will be 0. There's only one frequency where the amplitude is there. Okay, so you will get one. So if I were to plot, so let us say this is some sort of an amplitude versus frequency. So you will find that it is amplitude is 0, and this is one frequency where the amplitude is non-zero. This could be a sharper spike. Okay, so it was like non-zero, and then it is 0 here. So this is the frequency, only frequency component that you have, and that frequency component you can check from the signal versus whatever you are reading here. That can be simple verification that you are doing this Fourier transform correctly. Now, once you go from here to here, what do you see? Maybe you can see that there is still this one frequency which is there, and then you can see that there is another frequency which is here as well. So what we are trying to say is now what you would find, and that is an example what these sort of flows exhibit. Okay, these flows exhibit, and that's why I have brought in this example. Okay, you will see that this flow will exhibit a behavior from a single frequency to two frequencies maybe. So you'll find that there's one frequency and there is another frequency, and that frequency you can see that there is one thing which is taking it like this, right? So it is doing it overall amplitude, let us say, is going up and down. So that is one frequency that you have, and then within that frequency you will have that there is some high frequencies in there. Okay, so you can see that there are two frequencies which are here in the signal. So if you were to do again take a Fourier transform of this, you will find that there are signal will now become something like this here. Okay, now what happens in a turbulent flow? So multiple frequencies, and not just multiple frequencies, there is a whole range of frequencies that you would find. Okay, so there is a minimum frequency, there is a maximum frequency, and in between all frequencies would exist, not just few frequencies. Okay, so if you were to now look at a turbulent signal, so this is the same thing that is being plotted, only these axes may look a little bit strange to you, so we will not bother about them. Let us say that you have plotted something similar to this amplitude versus frequency sort of a thing. Okay, so you will find that now instead of just having two, and you put it on a log scale. Okay, so if you were to put it on a, you will find that there are all these frequencies which are active now. Okay, so all these scales are there now. Okay, so that is what, so that's why I'm just trying to explain you from laminar, if you go to turbulent, what happens. So you go from 1 to 2 frequencies, maybe to multiple frequencies, and then very quickly, so the transition from 1 to 2 happens, you can control that. You have a control parameter, you can control that, maybe a Reynolds number. If you increase the Reynolds number, you will see very clearly one frequency changing into two frequencies. Okay, and that is what you can see, for example, here as well. You can see this intermittent state very clearly in between. Okay, but after that, how will two frequencies change into three frequencies, four frequencies, five frequencies, and multiple frequencies, and then they will merge? All that happens in a very, very short range of Reynolds number, which is not necessarily, we can even control it very well. Okay, so you can very quickly see that transition happening from turbulent flow to, from this instability to a turbulent flow. But again, what I'm trying to explain you here is that there is always a transition, as we had said, and therefore things are always going to go from a laminar to turbulent in some smooth manner. Okay, in some continuous transition is there. Okay, it's just that the transition may be very fast or very abrupt, and we may not be able to see things very clearly, but there in principle there should be a transition that we expect to have. Okay, questions here? So this is basically, if you were to look at a turbulence, and we said that a turbulent signature. Now we can explain you one point that I keep making, that is this flow. So is this flow laminar or is this turbulent? So I have, what we have here is there is an object. Okay, there is a vortex shading which is happening behind this object. Let us forget about the other things at all. Let's think that this is all uniform. There's only one object which is there, and it is shading vortices. Is this flow laminar or is this flow turbulent? Okay, it's turbulent. So I've already said what is required for, okay, so now think of that, what are the features of the flow that it should exhibit. Okay, one feature which we have said, which is very important, is whether, if I look at the frequency or the spectrum of this, okay, if I take a Fourier transform and I look at what are the frequencies, will it exhibit one frequency, two frequencies, or finite frequencies, or whether it will give me infinite frequencies. Okay, so that is one of the infinite means, of course, within a range. Okay, but it is all frequencies in between. Okay, so so what do you think now from this point of view, if you were to look at this flow? The flow is laminar because it is only going to give me one frequency here, which is the vortex shading frequency. Okay, so you can see that is why flows like these, although they are now becoming unsteady. Earlier the flow was steady. Okay, now this flow has become unsteady. Okay, but it has not become turbulent yet. Okay, so any flow which exhibits this sort of a time varying behavior or exhibits flow separation does not mean that the flow has become turbulent. Okay, and this is an important point that I would like you to understand, and so that next time you are not just going to make a very offhand anything which is varying, oh, it's turbulent flow. Okay, we have so many people, if you look at how people in biology write it about flow of blood in our body, everything is turbulent for them. Okay, because wherever there is a connection, one artery changing its shape or size or whatever, so we'll have two arteries like this, one artery like this, let us say, and going suddenly becoming enlarging its size, or maybe coming in the other direction. Okay, and maybe there is some flow separation which is happening, or maybe if you have something like something like this here. Okay, maybe there are some vortices which are forming here, and then they will say that, okay, there are flow regions of flow separation, and that is my flow which has become turbulent. Okay, so you can see that this is all not correct. Okay, this all flow is still very laminar. Okay, if there are regions of flow separation, okay, there are maybe vortices are again forming. The flow may be unsteady in those regions, but that does not mean that the flow has become turbulent. Okay, so as we said, that what is required is that we can look at the spectrum, and the spectrum is one of the very good signatures. So if you see, only if you see a signature like what has been plotted here, okay, if you see a signature like this, then you know that the flow is turbulent. Okay, and what it will involve is, now you can think of that there are these frequencies. So these frequencies are, as we saw here, what does it mean? That things are happening at different time scales. Okay, so there is one time scale which is here, there is another time scale which is here. You understand this time scale? So something which is happening very rapidly, which is what is being given here, and something which is happening more slowly here, which is like I'm here at this amplitude, I increase my amplitude, I come down, I come to this amplitude, and then again I will start increasing, and then I will do that. So you can see that this is a much slower process, as compared to whatever is happening here. So here I keep on changing my state very, very rapidly. Okay, so you can see that there is a time, a low, a small, there is a rapid process and there is a slow process. Okay, but there are two processes only. One is very rapid, the other one is very slow. Okay, and that is what is corresponding to my two time scales, which is what I would see here in my spectrum, right? So, in a turbulent flow, you will find that there are lot of different, now if you were to now relate what is happening here to whatever you would see, is you will find that there are things which are, now we have talked about vortices, right? We have talked about the overturning, I mean they are moving in certain, they have a strength gamma, right, and which will sort of dictates how fast they are rotating, etc., right? We have seen the relationship, it is related to V theta now. V theta was related to gamma by 2 pi r or something, right? So here you can see that if you, so you can think of what is bringing about these events. Okay, you can think of what is causing these up and down of this. It can be happening because there is a vortex, okay, and there is some vortex which is rotating very fast, there is some other vortex which is rotating very slow. Okay, and therefore there are two types of, let us say, vortices, and that is giving you two different frequencies. Their rotation at different rates is giving you two different frequencies, right? So again, I am just trying to motivate, okay, as to how we start thinking about turbulent flows. Okay, and then once we start getting into turbulent flows, what we are saying is that now there are going to be lot of vortices of lot of different sizes, lot of different strengths, which are now rotating in the flow. Okay, so you can see that turbulent flows are always going to have lot of vorticity, and the vorticity is not going to be of a given size or a given strength. Whereas here, if you were to look here, what is going to happen is that always the same size and same strength of vortex is going to be forming every time. Okay, so this process is going to be very repeatable in this case, whereas in turbulent flow you will find that that is not repeatable at all. Okay, so again, just trying to give you some sense of what these turbulent flows would, how the flows would look like. Okay, so I think this is where before even trying to do some analysis or to understand the turbulent flows in a mathematical way, I am just trying to explain to you physically as to how we start thinking about turbulent flows. Okay, so I think this is where we will stop. We are already out of time for today. So we will come back in the next class and we will start looking at the problem of closure and other things in turbulent flows.